Hi, everybody. My name is Julia, and my research focuses on the development of cost-effective RF shields for 21.1 Tesla MRI probes. In summary, I constructed radio frequency shields using copper laminates to lower machining costs and improve image resolution. The aim of this work is to evaluate RF shielding performance on bench and in the magnet. Starting with an introduction to the radio frequency coil, RF coils are designed to transmit and receive RF signals to generate high-resolution images. In this project, I used a low-pass birdcage coil design. In combination, RF shields block external interference such as eddy currents generated by the gradient from coupling into the RF circuit. Currently, RF shields are manufactured by outsourcing to electroplate them, which costs us about $600 per part. The goal of this project is to replace the traditional electroplating process by using copper-clad laminate of 35 micron copper thickness. Moving on to my methods of shield construction and evaluation. G10 fiberglass formers were constructed and sty cast, which is a two-part epoxy, was used to bond the copper laminate on the inner diameter of each former, leaving a 2 mm gap between the starts and ends of the laminate. In order to effectively prevent eddy currents from coupling into the circuit, each laminate must form an electrically continuous loop, which is why I developed different prototypes using 6040 solder, silver epoxy, and gold leaf as variations to join the 2 mm gap. In addition, I created a fourth variant that eliminated the 2 mm gap and pushed the start and ends of the laminate flush with each other. To evaluate shield performance, I measured the S21 parameter using a vector network analyzer and near-field pickup loops. As you can see in figure 6.2, this bottom pickup loop is placed into the center of the B1 field where the sample would sit, and this top loop rests on top of the RF shield simulating potential eddy currents. Current is supplied from the VNA to each pickup loops, which causes them to generate their own magnetic fields, but also couple with each other. And inserting the RF shield in between these loops allows me to measure how effective the shield is in preventing these two loops from coupling. In the 21.1 Tesla magnet, I use echoplanar imaging sequences to evaluate for three main parameters: ghosting artifacts, reference power, and echo time. EPI features fast switching gradients, and every time the gradient is turned on and off, it generates eddy currents faster than normal sequences. Moving on to my results, it is clear that the copper-clad laminate shield joined by silver epoxy performed best in all areas of evaluation. Taking a look at magnet parameters, the only model that did not perform competitively against the electroplated reference was the no sealant model that exhibited a significantly lower QASNR and a high reference power. And finally, in conclusion, RF shields built with 3525 copper-clad laminate and joined with silver epoxy performed the best in all areas of evaluation. Other than the no sealant model, all other copper-clad laminate shields actually outperform the electroplated reference in SNR, which indicates that copper laminate is a functional alternative to electroplating and helps us lower machining costs from $600 to $50. Next steps in this research are to improve the application methods of both solder and gold leaf variations and create new variations such as the slotted shield with the use of fixed capacitors. I would like to thank my mentor Malky for supporting this research all summer and my peers in the REU program for a great summer. Thank you.